Welcome to our first one.
The biggest thing was.
Hello, everyone.
Mine's free. That's like really big. I give me the $500.
Good afternoon, everyone.
Thanks.
Okay, welcome to the last seminar of the term. Christmas, yay! Or sorry, happy holidays, yay! Okay, so last seminar of the term, we have once again 3 speakers. Unfortunately, one of our speakers is joining by Zoom. Hopefully she feels better soon. But our first speaker is Abdelmoneim Naggar, who will be speaking to us about effects of design provisions on the response of reinforced concrete frame structures to foundation settlements. So with that, please, the floor is yours.
Thank you. So today I'll be talking to you about a portion of my research, which was basically studying the effects of Canadian design provisions on foundation settlements for concrete structures. So we'll be starting off a brief introduction. Then we're going to list our objectives and the modeling approach that we followed basically to reach these objectives. We designed according to 3 different seismic areas within Canada: Victoria, Montreal, and Winnipeg. You know, high seismic hazard, medium, and low. Then we're going to go on to our results, and finally we'll end off with some concluding remarks. So, differential settlements could be caused by various factors, including vibration, liquefaction, for example, or consolidation, or even a nearby excavation. Like over here, for example, you can see this column got major vertical cracks due to nearby tunneling activity in Istanbul. And so this differential settlement, what it does is that it basically imposes a new stress scenario on the foundations within pre-existing foundations in the area. So you'd be experiencing new axial and lateral forces, which were not accounted for in the design procedure, right? Because when you look into the National Building Code of Canada or the American Concrete Institute building codes, you're given wind provisions on how to tackle wind load, seismic load, and of course, dead and live loads and stuff like that. But we're not really given a clear provision on how we should tackle settlement loads. So this new stress scenario, the new stress scenario could affect your structure and possibly damage it, and maybe even jeopardize, your whole structure. So the objectives of this study today was to study the redistribution of the loads within a structure and look at the effect of the support loss within a reinforced concrete structure and the effect of that on its performance. And finally, look at the effects of the Canadian design provisions on the overall performance of that reinforced concrete structure. You can see over here how, severe differential settlements could be on a building. Like you see, even though this is a pile foundation, it's still experiencing a significant tilt over here, right? So, as I said before, for our design criteria, we looked at 3 different seismic areas within Canada. So high seismic areas in Victoria, and the medium seismic area would be Montreal, and the lowest seismic area in Canada is Winnipeg. And so we designed basically for a 6-story building. This was a residential building, so the live load was 1.9 kPa for each floor. And this is a typical reinforcement scheme that we used for the beams, for example. And these are more details about, the individual structure that we designed and different cross-sectional lines that we have for Victoria, Montreal, and Winnipeg. So in order for us to achieve our objectives today, we use something called Seismostruct. Seismostruct is a final element software that uses a fiber element approach method. So what it does basically is that it includes the distributed plasticity within the elements, and it accounts for the material nonlinearity and geometric nonlinearity. And for us to check and make sure that it's going to suit our needs, we first validated the basically the results from Seismostruct against a beam that was casted here by Dr. Youssef and his research group in 2008. So as you can see over here, this load deflection diagram shows a great agreement between the experimental results and the results that we obtained by Seismostruct. So we divided the columns into 6 elements and the beams into 3 elements, and then we use the same, division of elements all throughout our bigger frame structures. So the first thing we did is that for the structure that we designed, we made it subjected to a differential settlement of the middle column. So for us to do that, we put the building on springs basically, and we incrementally decreased the spring stiffness in the middle for it to settle basically and experience support loss, similar to what it would experience, for example, in a tunneling activity. So over here, you can see the axial moments that were experienced at 1 bay away from the settling column. So usually 1 bay away from the settling column, that is where you experience your maximum damage. And so over here, you can see, for example, the reaction forces at 1 bay away from the settling column increased by 60%. So even though the magnitudes differ, the trend for Victoria, Montreal, and Winnipeg was the same. And you can see over here the phenomenal increase in moments that was experienced by each frame. So this adds a whole new loading scenario for your structure, and it makes sense that the structure would be damaged after these new loading scenarios. And over here now we also basically investigated the effects on the edge column, so 2 bays away from the settling column, which is, let me show you over here. So we found out that the building basically experiencing some sort of a seesaw effect, where as this column settles, the column over here takes on the load that is being lost by the support, and over here you get experiencing an overshift, like an uplift, which is basically like an increasing moment on the overall middle section. So again, as you can see over here, the reaction forces are decreasing in the column 2 bays away. However, the moments are increasing. And again, even though they're increasing by different magnitudes, they're all experiencing the same trend. And this shows the maximum settlement that will be experienced by each frame, designed according to the seismic region of Victoria, Montreal, and Winnipeg, which is SC3 according to MBCC. And so basically, as you can see over here, the design provisions do have, a noticeable effect on the performance of the structure. So Victoria, which is a highly seismic hazard, was designed according to section 19 of the Red Book, for example. And you can see that it has a greater resistance for differential settlements when experiencing total support loss. While Winnipeg, which is a conventional design, what we usually see for residential buildings, it went up till 55 millimeters. So after that, we looked at 2 different loading scenarios. So we looked at a support loss at an intermediate column and a support loss at the edge column to see the effects and whether or not we're going to see the same results as the middle column or not. So we can see over here the maximum settlement experience for each loading scenario. So the edge column went through a greater differential settlement, going up to 83 millimeters, as we can see, and it went through more damage. And that could be attributed to the fact that, the center column, basically when it settles down, you're changing the loading scenario, but it's more like a simply supported beam now, because you lost that support in the middle. So it's more like a simply supported beam, while at the end, it's more like a cantilever type of loading. So as you can see over here, even though we have the same trend, the magnitudes are different. So you can see the edge column, for example, it experienced an increase by 80% in reaction force, which is huge, basically for, loading scenarios. So, yep. So as we saw, foundation settlements could result in serious damage to structures, and the redistribution within that structure it could significantly impact the performance of the overall building. And for us to, building codes right now don't have a specific clause for settlement. However, we saw that the seismic provisions had a great effect on that performance. And therefore, we need to understand the seismic hazards and how they can help us in providing a greater resistance for these support losses. So thanks for listening to my presentation. I hope you enjoyed it.
Thanks for that presentation. Any questions for Abdelmoneim? No questions. Okay.
So for the-
Sorry.
Yeah, for the different settlement. Because you start with the column that's in the middle, right? So you just assume like a random settlement that's happening in the middle?
No, we had it decrease incrementally up till zero support. And we chose one settlement, or like one settling column only at a time, because that is what the code looks at. So there's another section of the code that gives you an angular distortion limit. So angular distortion limit is basically, like the difference between two settling columns in a bay. So that's why we took out one settling column incrementally up till support.
So there's no specific stratum under the foundation, right?
Oh, no, these were springs.
Those rings.
We later on included the more specific strata, but this was the
Okay.
preliminary phase of my research.
Yeah.
Yeah.
Other questions? I had just one that, you talked about in your final unlock, you incorporate material nonlinearity. What do you mean by that?
The concrete was modeled using a consistent model by Mander itself. I think it was in 1988, if I'm not mistaken. And so the seismospect is basically like open seas, if you heard of open seas.
Yeah.
It includes material nonlinearity, like it has constitutive models that are able to account for the nonlinearity of the steel, of the concrete and stuff like that, and show you where it's crushing and where it's cracking. And
So how does the concrete material constitutive model behave post-peak?
oh, it's like a cyclic behavior of the Mander et al.
Oh, it's.
Yeah, it's like
specific
cyclic.
for this.
Yeah.
Okay, excellent.
Yeah.
Other questions? Okay, thank you very much.
Thank you very much.
Okay, Ezra, can you try and unmute yourself?
Yes.
Could you try speaking?
Hello.
You try sharing your screen?
Please, I feel also.
Our next speaker is Esraa ElSayed. Sorry if I mispronounce your name.
No, that's correct.
Who couldn't join us in person today, but she'll be talking to us about her investigations into the interactions of various accelerators and cement-based shotcrete mixtures, supervised by Professor Jiahao and Naggar. With that, please, the floor is yours.
Okay, thank you. Hello, everyone. My name is Esraa, and as Dr. Wang says, I will be presenting my research entitled Investigating the Interaction of Various Accelerators and Cement-based shotcrete mixes under the supervision of Professor Naggar. So in this presentation, I will first start by the introduction and a brief literature review to give you a hint why we have a motivation and we are interested in this research. After which, the list of our objectives will be listed, and then I will walk you through the methodology, which includes laboratory testing and the field study. And then I will introduce a brief summary of the results and the analysis. As you can see here, first, the shotcrete is a form we can identify as a form of a mortar or concrete placement in which the material is pneumatically projected at high velocity into a vertical or overhead surface. And it's just a nice way, or it's like a faster way to be used in many geotechnical applications, including but not limited to tunneling, as you can see in here, and also ensuring and supporting excavations or vertical and slope cuts. And the basic material used in shotcrete similar to those used in the conventional concrete. So we're still using cement, supplementary cementitious material, and super plasticizers and so on. However, the key element or the fundamental additive in shotcrete is the accelerators, as the accelerator provides the rapid setting and the hardening properties for the shotcrete. And the accelerators can be divided into alkali-free and alkali-containing accelerators depending on their chemical composition. And in literature, several accelerators have been studied. As you can see in this table, it just illustrates some of the types of the accelerator along with the chemical composition and mode of action and the recommended doses, which range between 2.5 to 6%. Sorry. And accelerator effect on the early strength depend on the chemical-based dose, but also on the temperature, as the accelerator alters the kinetics and the mechanism of the cementitious material hydration. So, for example, if we are talking about the alkali accelerator, such as the sodium silicate, this accelerator will accelerate the hydration of the C3A and the C3S, promoting the CSH gel, which will lead to the early setting and hardening properties. While if we are talking about the alkali-free accelerators, such as the aluminum sulfate, this will accelerate the hydration of the C3A, promoting the early formation of the needed eternite. At the end, this eternite will connect together and also accelerate the setting and hardening properties of the shotcrete. Despite this advantage of the early strength, still the shotcrete mixes are exhibiting a varying level of loss of the compressive strength, especially at the 28 days after the curing. And several researchers reported that especially the alkali accelerator, the sodium silicate one, is losing between 20 to 40% of its strength. And this leads to the widespread and the popularity of the alkali-free accelerator as an alternative. However, the alkali-free accelerator still has its own disadvantages, such as the high cost. From here, what motivates our research is first the loss of the compressive strength and how to solve the compatibility issue between the accelerators and the cement matrix, and also the need to just introduce in the market new silicate accelerator that's environmental friendly, but that at the same time will overcome the deficiency of the long-term compressive strength reduction that we are suffering from nowadays. And also, so our objective is to evaluate the performance of the shotcrete mixes with silicate-based and alkali-free accelerator, also to investigate the mechanical and microstructural properties of these mixes at different curing time. And we will introduce new sustainable silicate-based accelerators that better serve the different geotechnical applications and overcome the drawbacks of the existing shotcrete mixes. We did a comprehensive investigation program just to fulfill this key objective. First, we started with the preparatory testing, and after just having the right mixes and make sure that we get the target compressive strength, we did a field study by shooting these tested mixes in the field, just to to simulate what we have in the field, like the tunneling project and so on. And in this, in here, I will just discuss the field study just to be within the 12 minutes. So for the field study, we used two commonly used shotcrete mixes, was adopted in this research, and shotcrete company was hired to spray the panels. We did use two silicate accelerators, the new innovative alkali silicate accelerators with high silica ratio of 4.5 and normal silicate accelerator with silica ratio 3.3. We did use, for a comparison, commonly used nowadays in the market, alkali-free accelerator, aluminum sulfate one. And we have two control mixes. The first one, as you can see in here, is a mortar mix, including GUL and fly ash and microsilica, while the second mix including GUL, slag, and microsilica with stones less than 30 milli. And a total of 8 shotcrete mixes have been sprayed using water cement ratio of 0.43. The early compressive strength of the mixes was taken using the end beam tester, while the cores from the panel were used to get the compressive strength at later age from 3 and up to 90 days. Then these specimens were used to get the microstructural analysis doing the XRD, TGA, and scanning electronic protocol. As you can see in here, we have total of 4 mixes with 2 shot crate control mix. So a total of 8 panels have been sprayed, as you can see in here. And after spraying, the panels were covered with wet burlap to ensure good initial curing. And of course, we had an environmental challenges. The weather was so cold, so we used an insulated blanket and a heater all the time just to keep the panels at the target temperature until we can flip it and get the cores and move it back to the lab. As you can see in here, this how we get the core, and this sample is from the end beam tester that was used to get the early compressive strength at 6 hours. In here, quickly, I can briefly say that for the high ratio silicate accelerator, we can see at 4% increasing, we will see that the compressive strength is increasing with time up to 90 days. And we have similar behavior by increasing the accelerator dose up to 6%. However, we can note a slight reduction in the compressive strength at 56 days, but still followed by a peak at the 90-day. Similar behavior to this high ratio silicate accelerator, 6% is observed for the alkali-free accelerator, even with similar values. So from here, we can say that the new silicate accelerator have a competitive behavior to the alkali-free accelerator used in the market nowadays. And finally, we can say that the standard silicate accelerator is showing also increasing of the compressive strength with time, but with relatively lower compressive strength values compared to the other accelerators. And in general, we will see that these 3 accelerators working the best with the first mix that include high content of the cement, fly ash, and microsilica, and having similar behavior but with less values of the compressive strength when we add a slag to the mix. So if you are recommending a mix to the industrial partner, we're going to recommend the one that have GL, fly ash, and microsilica, because no matter what accelerator we use, we're still getting the target compressive strength. And to further understand the compressive strength behavior, we did an XRD and TGA on the specific sample at 56 and 90 days. Samples were taken from the core. The hydration was stopped by adding acetone, and then the specimen were prepared to be tested for the XRD and TGA to get the mineral phases. From here, quickly, we will see that at 56 and 90 days, like at 56 days, there's no significant difference in the hydration products between the different mixes. And from 56 to 90 days, we'll even see no significant difference. So the XRD data didn't explain much what happened in the compressive strength behavior, because we expected to have like a significant hydration product because we have a significant increase in the compressive strength, but this is not the case in here. Even having the TGA results, we will see that there's no significant weight loss between the different mixes. So from here, we can say that we still have a good new accelerator that's competitive to what we have nowadays in the industry market, but we still we don't have much explanation what's happening and what's the compatibility issue of the old silicate accelerator. So we are suggesting that there is like another factor dominating the compressive strength behavior. It might be the pore size and distribution. So we're still working on this. Hopefully we'll find answers. And these are the references. Thank you for listening to the presentation. We'd be happy to answer any questions.
Excellent. Thank you very much for this presentation. You received applause. I don't know if it came through the microphone properly. So are there any questions from the audience? I can pass it on to the speaker. Yes.
For the methodology, why was a water cement ratio of 0.43 used? Was it determined as the optimal ratio or just as a basis?
Okay, so the question was for the water to cement ratio, why was it 4.3%? How did you decide on that number?
Usually when we are using for the underground application like tunneling and mining, they are using low, and for the shotcrete especially, we are using low water content because you're already using super plasticizer and air in training. And for our mixes to be like applicable in the field, we have to go exactly with the mixes that the contractors and the company is using already, and they were using at this project water cement ratio of 0.43. And usually for shotcrete, it's not going higher than that.
Excellent. Thank you. Other questions from the audience?
So what is the maximum thickness that you can use for for this type of concrete?
Yeah, so the question was, what is the maximum thickness of shotcrete that you can pull off, you can manage?
As of my knowledge, there is no limit because nowadays you can even shoot 2 and 3 layers on top of each other. So for this application of tunneling, there is no limit.
Okay, excellent. Thank you. Other questions from the audience? Okay, excellent. Thank you very much, Esraa, and hopefully you feel better.
Thank you.
Okay, so you stop sharing your screen? Thank you. There. Okay, so our third and final speaker of today and the term is Wang Jiahao. Yes, excellent, thank you. Who will be speaking to us about water evaporation and condensation during smolder. And he's supervised by Chris Power. Excellent. Please, the floor is yours.
Okay, good afternoon, everyone. I'm the PhD student in environmental engineering. Today, my topic is about water evaporation and condensation during smoldering. It's a very great honor for me to present here. But first question, what is smoldering? Smoldering is flammable combustion occurring inside porous media. And the porous media is something like sand, soil. It has some pores within that structure. And a common example of smoldering is growing charcoal in barbecue. As you can see here, when you see charcoal bouquets growing red and slowly burning away, that is the process of smoldering. And as seen from this charcoal barbecue, smoldering has the potential to be self-sustained. So once the charcoal is ignited properly, no more external energy is needed to support this smoldering reaction. And therefore, that smoldering fire are extremely challenging to be distinguished. Sometimes they are called zombie fires. So that includes the wildfire in the peatlands. I think this year in Canada, it has been reported we have over 6,000 wildfire in Canada. And these wildfire are particularly difficult to be put out despite extensive winds. And we also have coastal fires under the ground. Some of these coastal fires can burn over 100 years. And we also have the smoldering fire of the wooden structure. As you can see, it's during the winter, surrounded by all the white snow. However, several feet of snow still couldn't prevent smoldering, destroying this wooden structure. Now, some fire researchers study the smoldering of the polyurethane foam. Because polyurethane foam is commonly used in the household, such as furniture and some mattresses. So traditionally, you can tell the smoldering is considered a serious fire hazard. It can cause a lot of damage and losses. But however, we are from the environmental engineering. So we start to think if we can take advantage of these zombie fires to help us for the environmental beneficial purposes, such as destroying contaminants in the very challenging conditions. And the answer is yes. So today, smoldering has been efficiently proved to destroy the coal tar and hydrocarbon contaminated sites. So basically, in this context, coal tar and the hydrocarbon, they are the fuel, they are the coal tar for the barbecue, for the smoldering here. And the process is quite straightforward. You basically figure out where's contaminants, and then inject hot air to ignite these contaminants. And as you can imagine, once these contaminants are burning, the smoldering will spread following the injected airflow, destroying contaminants. It goes until the whole site is clean. But that is photo comparing the oil contaminated soil before and after the smoldering treatment. As you can see, all contaminants are removed by a very high temperature from smoldering treatment. And besides, smoldering can also be conducting ex situ in a large containers. So we use these equipment to help us reduce some very challenging municipal waste, such as soil sludge, pebble mill sludge, food waste. So most of this waste, they have very, very high moisture content, about 60%, but with low heating value. So when you burn it, it's very hard to burn. Therefore, it's very challenging and expensive for the traditional thermal treatment. But we can do this a bit easier with smoldering. And we already have some pilot tests from the lab result. Nevertheless, although despite all the successful application and the lab experiment for the smoldering, we still don't really quite understand on this field, the wet smoldering, because only the laboratory work is performed, and we don't have much field studies and field cases, and also with limited mathematical understanding of how water is really affecting the smoldering reaction. Therefore, we cannot really answer the question like how wet it can burn. And that is something the industry will really care about. So that is the process of the self-sustained wet smoldering, where you can see the contaminants or embedded in the wet process media. So you can just assume that is sand. And just like how you do the barbecue at home, you need a heat to dry the material and let the material to reach ignition temperature. However, turning on heat only works to dry the adjacent bed, while the majority of system is still cold and wet. So water vapor will condense in the up cold region and increase the local water saturation. Only a small amount of water vapor can leave the system. Then the introduction of airflow with the local material above ignition temperature could initiate the smoldering reaction in the bottom of the pack. And that excess energy from the smoldering carries forward, which can support the water evaporation and the smoldering reaction to progress through the system without external energy. Because now the energy generated from the smoldering reaction is enough to cover all the energy consumption in the system. So at that time, heater can be turned off, and the whole system is at a self-sustained condition. And the water and the contaminants will be eliminated by the smoldering propagation, leaving only clean sand behind. So you can tell it's quite complex system because in that small scale, we have a smoldering reaction and also water evaporation and the water condensation. So it's quite complex. And in the beginning, we only trying to do the experiment to understand these mechanisms. So in this case, we also apply a very simple experiment. We use the granular active carbon, mix the sand and the water to make the white combustible material. So GAC, that is great sample field for our smoldering studies. It can burn and it's not toxic. And the chemistry is pretty simple. So we can use the one-step oxidation reaction to model the smoldering reaction. And the experiment procedures basically follow the same animation you saw in the last slides. So we put all this white mixture into a 1 meter height and 10 centimeter wide stainless column. The heater and the air sponger were placed in the bottom to trigger the smoldering reaction. And the thermocouples, the black dots, thermocouples located in the center of the column were used to measure the temperature changes. So the temperature can help us to monitor the water evaporation, condensation, and smoldering in real time. And these experiments were used to validate Wendy model. So in this Wendy model, we consider water evaporation, water phase change, basically, and the GAC smoldering. This function was solved by these equations, Galvin equations. So we solved the mass conservation of GAC, liquid, water vapor, oxygen, and total gas. And the water phase change was solved by this non-equilibrium phase change simulation. So basically, you can see it's governed by the saturation, water vapor pressure, and the vapor pressure. And the momentum balance, basically the velocity of the gas was solved by Darcy's law. And we use two different energy equations to solve the temperature of the sand and temperature of the gas. We used console software to solve all these equations, and Now it takes about 2 days to finish each simulation. So this is the simulated results. So the left column have the predicted temperatures, and the right column we have the water saturation data. So basically, you can see water is removed from the heat wave from the heater, and also it's driven by the smoldering propagation. So you can see that is smoldering propagation. However, all this water removed by the heat wave, we condense on the top region. So you can see top region, actually we're increasing the local moisture content. And that process keeps going, continuously increasing the saturation on the top until the smoldering front approach there and drives that air. So that water recondensation is a key feature, and also it's a great concern for the smoldering application. Because of this water recondensation, in that area, we may reach a very, very high water saturation, and that smoldering can never overcome, and that causes the extinction. Besides, you can see here, the effect of water phase change is spread throughout in space and time. It's quite difficult to quantify the effect. But recently, our research found actually all these reactions, they propagate through the system in a relative same velocity. Therefore, the whole wide smoldering front could be divided basically into two regions. So you can see it's red region, that is smoldering region, that is hot, dry, and clean. And we have the blue region that is in front of smoldering region, that is cold, wet, and contaminated. So our key question is, if this smoldering reaction is strong enough to remove all the water and destroy the contaminants in the upper regions. Actually, that answer closely relates to a key area between these two regions, namely the preheating zone. So preheating zone is in front of smoldering front, but behind the wet region. So basically, preheating zone serves as the important dry buffer, protecting the smoldering from water quenching. If we don't have that preheating zone, water will directly attack the smoldering and cause extinction. Therefore, the thickness of this preheating zone is significant, which was found to decrease with the increase of the initial water saturation in the system. And it requires a minimum thickness to avoid smoldering extinction. That is 4 millimeter under 70% water saturation in our case. So that observation is quite valuable for the industrial because, for example, in the field site, given the water content of the field and also given the type of contaminants, we may be able to use this model to predict the preheating zone during the smoldering treatment. So basically, we can know if the smoldering will be foreseeable under that condition before we start doing everything. So that will save our lot of money and time. So in summary, this study is the first to systematically evaluate water evaporation and condensation in the smoldering process and reveal a significant role of the water on smoldering application. The structure of the wide smoldering front was identified where the preheating zone is significant, crucial for the successful smoldering. And water is negatively affecting the smoldering reaction by suppressing the preheating zone. In the end, as we already know, the preheating zone is significant for the wide smoldering. So maybe that area can be manipulated by the engineers by changing the operational parameters. For example, the airflow, fuel concentration to change the preheating zone to avoid smoldering extinction. So that's basically all. And I want to thank everyone in these slides. We have some in the first. I want to thank everyone in these slides. They really worked really hard and closely to transform a smoldering application from very, very small experiment to a real world application. Basically, first smoldering experiment, they start from the beaker, and now they are applying to a very wide field site. And in particular, I want to acknowledge my supervisor, exceptional mentor, Dr. Jason Jiahao. His passion and the perseverance really lighted this research. Unfortunately, he's no longer with us, but his passion, kindness, and legacy will live on. Thanks so much.
Thank you so much, and thank you for recognizing Professor Jiahao. That's great for you to do and for all of us to remember it as well. Do we have questions from the audience? Yes.
Thank you for your presentation. Does the smoldering have any effect on soil estuaries? Let's say we have petrochemical facilities and the soil beside this facility is contaminated, and you use a smoldering to clean the soil. Is it any possibility for the facility to experience displacements or settlements after you clean the soil?
Yes. So basically, you can tell the smoldering is very high temperature to 900. So basically, we remove all the organics from the soil. But that's why we only use smoldering for the very high contaminated sites. So like oil and coal tar, something like that. So basically, we don't have any organics or features in the site, so we can remove all the stuff. But now people also are studying if we can after the smoldering treatment, if we can input some nutrients into that post-treatment sand to see if we can reuse the sand for the agriculture, furniture, something like that. But for now, we basically just remove everything, we burn everything.
This is the nutrition part and agriculture part. But my question related to the strength of soil.
The strength of soil.
Strength of soil.
Yeah, because strength of soil, because basically we burn everything in the soil. So if the sediments, like basically strength compares many stuff in the soil. So if we burn everything from the soil, for example, it has water, but now it doesn't have water, and they have like nutrients. If it have some sediments, now it doesn't have sediments, for sure it will affect the structure. The strength of the structure, we don't really measure that, but I can tell will affect for sure.
Thank you.
Yes, no worries.
Any other questions from the audience? So I had one, really naive one. So in the examples you showed, you're talking about the zombie fires that they're trying to get it to stop. But then here you're talking about how to prevent extinction of the. So what makes it different that one we can't stop at all, and this one you're trying to keep it going? What's the difference?
So it's actually no difference. So basically we have the delicate balance here. So on the left side, we want to stop the smoldering.
Right.
So we want to increase the water content to stop smoldering. But that is for the fire hazard. We don't want smoldering.
Right.
But because of the smoldering is very called zombie fires, it's very hard to die. We can use that feature to help us to destroy the contaminants. So in the application, we don't want smoldering to die. We want smoldering to survive to destroy the contaminants.
Okay, so and that's just controlling the moisture content.
Controlling moisture content. If for the nature lesson, we don't want smoldering. But for diarrhea, we want to survive.
Like a dial. Okay, excellent. Thank you. Any other questions from the audience? Okay, thank you very much for your. Oh, sorry, there's one.
I might have missed it, but this is for like cleaning purposes, like you're trying to clean the granular of contaminants by using smoldering. And so while you're controlling the moisture, you're artificially saturating the soil to reach that specific amount to have a good smoldering behavior.
So basically in the field, we cannot control the moisture. But in this material, we can control the moisture. So now we focus on like extension. So we take the material from for example, from the wastewater treatment for the soil sludge. We can control the moisture before we apply the smoldering.
Oh, that was my question specifically with the oil sludge one. So it's like oil sands, right?
Oil
sands saturated in the sand.
Yeah.
So then you want to increase the moisture or you want to control it. So are you adding any water to that? Because then the water and oil aren't mixing.
Because oil sludge, I think some industrial oil sludge, they actually, although they call it oil sludge, but they have very small amount of oil, but with a lot of water.
Oh, so they're mixing more sand into the
Yeah,
the oil?
so they have the oil, I think it's 4%, but 96% is water. So we try to see if we still can use smoldering to burn that oil. Cool. Thank you.
Thank you. Okay, so thank you to all of our speakers today. And also thanks to Sabina, who's kindly agreed to judge all the presentations. So it's just not just my scores that are coming into the decision of who gets money, basically. So with that, thank you all. Thank you to all speakers, to Sabina, to all of you for listening, and happy holidays.